Welcome to the OpenCL tutorial series. My name is Dave Gohara, and I'm with MacResearch.org and also at the Center for Computational Biology at the Washington University School of Medicine. This is the third episode, and in this episode we're going to talk about how to build an OpenCL project. We'll talk in a little bit more detail about some of the key functions and functionality in terms of what you can do in setting up your calculation, and some of the tools that you can use briefly, like Xcode, for building projects, running your calculations, building applications that will use OpenCL under the hood. We'll also start off, though, with, like in the previous podcast, with some Q&A. There have been a lot of really great questions posted to the MacResearch.org website or via email to me. So I'll address some of the more common ones. And then certainly if you have any more questions, or if you have questions about some of the stuff that's presented here, again, feel free to post to the MacResearch.org website or send an email to me. I'm also on Twitter, so if you want to send it via Twitter, feel free to do that. It's, of course, 140 characters or less, so it'd have to be, I guess, a short, simple question. But anyway, there's multiple ways of getting a hold of me, and if you have any questions or comments, certainly feel free to send them along. I'd like to start off again with a little bit of housekeeping. I want to thank our hosting provider, Macias. Certainly over the last week or so, last couple weeks that whenever the series started, I guess this was last week, the traffic to MacResearch.org has really gone up, and I'm sure it's put a lot more bandwidth that we've been using, and they've been really great, great service, great support, and so I would really like to thank them. And if you're interested or looking for application hosting, server hosting, things like that, I'd really encourage you to check them out. They're a really great group of guys, and they've treated us very well. So I thank you to the guys at Macias. So let's start off with some Q&A. There were quite a few questions that either came to me directly or via posts on the website. And so I'd like to address some of the more common ones that have come in. And so that would be covering double precision arithmetic, which is important for a lot of scientific computations, object-oriented programming, and how that integrates into OpenCL, how you can use these things together, if at all. There was a question about asking for some clarification on global versus work group sizes, when you want to tune one versus the other, so we'll talk about that. And then generally, we'll talk generally a little bit about the classes of scientific problems that you can solve or work on using OpenCL, and when and how those might be appropriate. It's a little bit of a complex sort of discussion, so what I'm hoping is, to just kind of broach the subject now, and then over time, as these podcasts continue, maybe, hopefully people will get a better feel for the kinds of computations and calculations that they'll be able to do using OpenCL, or perhaps having to use a separate technology. So let's start off with double precision. Double precision in the OpenCL spec at the moment is optional. So the 1.0 version of the spec, it's optional. You need to know, there are a couple things that sort of determine whether or not it will be supported on a device or within an implementation. And there are ways to sort of probe the hardware and the implementation as well to see if it supports these sort of optional extensions. If you have hardware that does support double precision, and the implementation also supports double precision, there's a pragma that you can use and that you need to use before you issue any statements to double precision calculations. If you don't do that, the specification defines that double precision behavior is undefined. So depending on the type of graphics card that you have, or the implementation itself, it could just crash and burn. The calculation could just crash. It just may not run. You might get compile time errors during the kernel or program compilation. There could be a number of kind of behaviors, and it's very tough to tell. So you want to make sure that you're checking for these things, and that you're looking for them before you do anything that really relies or requires this to have happen. And so, like I said, double precision graphics cards. For example, CPUs we know support double precision. I mean, they have for a very long time. On graphics card, this is something that's a little bit more recent. And so if you have a very new graphics card, the chances are probably higher that it does support double precision. If the card supports double precision, the implementation also supports it, you're guaranteed that the implemented form will conform to the IEEE standard, just the same as, and so in terms of rounding modes and things like that, exactly the same as it does for single precision. So you're at least guaranteed that, but there's no guarantee that it's going to actually work because, again, this is an optional extension. Now, there's one thing that you do need to consider, especially for scientists if they're doing scientific computation and they really need double precision, is that there's a big performance hit that you take. So, for example, on the GTX 285 single precision floating point operations, you can get about 1,000 gigaflops per second, so about a teraflop per second of floating point computation in single precision. In double precision, because the number of floating point units for double precision are much less on each SM, you get about 90 gigaflops per second on the GTX 285. So you're talking about an order of magnitude performance hit. If you do have a graphics card that does not support double precision, or you're not really certain, there are ways to kind of get around this. You can kind of sort of emulate it using mixed precision math. And for right now, probably that discussion is a little bit beyond the scope of what we want to talk about here, but there's a link at the end of this podcast or if you're looking at the PDFs on the very last slide, that will take you to a really nice presentation that some people have put together and that's available online, that talks about mixed precision arithmetic and how you can use this to effectively emulate higher precision arithmetic on devices that don't support it, and also if you need this without incurring such a huge performance penalty. So that's double precision arithmetic. Hopefully that answers the question that was posed. The next question that was asked was in regard to object-oriented programming. So OpenCL obviously is derived solely based on the C language. So this sort of concept of object orientation does not exist in the language itself. What that means primarily is that you cannot pass complex objects into OpenCL kernels. You can certainly copy the memory blocks and things like that in there, but they're not going to behave the way that you'd want to. The JIT compilation that occurs on your kernels is assuming that this is C with the OpenCL extensions being supported, and that's it. So, for example, while you can call OpenCL routines from object-oriented programs, you can't pass objects in. So if you're using, say, C++ or Objective-C, your methods, say in Objective-C, can make calls out to OpenCL. They just can't pass any of the instantiated objects into the kernel. So what does that really mean? It means that, for example, let's say you have an NS array of NS numbers using Objective-C. You can't pass in that NS array and expect it to be utilized and to be utilized efficiently. I mean, even if it could take it, it's not going to be utilized well because an NS number is a complex object and there are all sorts of little things. What you can do, however, is you can have routines that might take all of the NS numbers in an array, convert them to floats, and dump them into a regular intrinsically typed array that OpenCL would understand. So that's any C any C array or any of the extended primitive types that OpenCL supports. You can pass those into the kernel, and then the kernel can process, the information and do whatever computation you want. And then when you come back out, you can put the number back, say, into your NS array or something like that. The important thing to keep in mind is that all of that extra overhead may or may not be of value to you. So you do have to evaluate those kinds of things. In cases like, in our case, for example, in APBS, where we're spending so much time doing the actual calculation parts, the little bit of overhead that we take in reformatting our data structures and things like that really doesn't affect us all that much, because it's just a minuscule amount of copying that takes place, and we sit and we spin and crunch on the numbers for quite a while. So that's not something that we need to we need to concern ourselves with too much. The one thing that OpenCL will support, it doesn't support obviously complex objects, it does support structures. So you can make complex structures as long as those structures are built up from intrinsic types from the C language or any of the extensions that OpenCL supports. So those types of things you can pass in and you can use, but if you're looking for any kind of any kind of more higher level object orientation, it's just not going to work in OpenCL. And this is actually slightly different, I think, from what you get with CUDA, where CUDA can kind of support where it does support object-oriented languages like C++ and things like that. So that's something that's very sort of important to think about, depending on the kind of project that you work on and how your data is your data and your data structures are organized. So continuing on, the next thing was workgroup sizes, and let's talk about that. Let's do just a little bit of just like a refresher. Let's say we're talking about an array of 16 elements, and our global work group size is going to be 16. The local work group size has to be some value less than that, obviously, and it needs to divide evenly into the global work group size. And so let's take 2 as an example. If our local work group size is 2, that means we'll have 8 local work groups, 8 work groups of 2 elements each. So just so we're all on the same page. Now, the one catch to that is that the local work group size on a CPU is it always has to be 1. And the reason for that is that it's a technical reason, and that's the ability to synchronize work groups. To have communication between work groups, you may have to do some synchronization, and synchronization points on a CPU to implement them are extremely expensive. The number that was quoted to me was somewhere around 10,000 cycles, I believe, to implement synchronization points, and that's I mean it's 0.68 seconds. It's really it's an eternity to the CPU. So it's actually not quite literally 0.68 seconds. That's a Star Trek reference. But the point being is that to CPU, 10,000 cycles is a very, very long time. And so you really need to kind of think about it in that way. So on the CPU, your local workgroup size always needs to be 1, or you need to set it to just set the value to null when you invoke the argument. So that's the thing. Now, on a GPU, how do you determine what the local workgroup size should be? And often, honestly, it's a little bit of trial and error. NVIDIA makes this Excel spreadsheet, this little worksheet that you can plug some numbers into, like the number of floating point operations, things, GPU type, probably clock speed, things like that. You can put in some numbers, and it'll give you some recommendations in terms of what your local workgroup size should be and things like that. But often, even with that, that's just guidance. You often have to go and you have to try a few different things just to kind of see what it is. Now, there's a couple things that you want to think of. Your global work size and your local workgroup size certainly should never be less than the size of a warp on NVIDIA hardware or of a wavefront on ATI hardware. So the on NVIDIA hardware, a warp is 32 threads, and we'll talk in great detail in other podcasts about warps and wavefronts. But basically, these are sort of units of work and how the GPU likes to think of things and process data in swaths of data as it's working on them. And so on NVIDIA hardware, the warp is 32 threads, 32 elements, and so you definitely don't want your workgroup size to be any smaller than that. On older NVIDIA hardware, actually, the warps used to get broken down into what are called half warps, so they'd be 16 elements each, but that's a hardware abstraction. On the latest hardware, it's not really done that way. I think they're done as full 32 element loads into the SM, so you don't have to worry about that. But that's your smallest size. Now, the other thing you want to think about in terms of work group size and things like that, powers of 2 or variants of powers of 2, where you say have like 2 powers of 2 added together or something like that, are typically your friend. But even numbers, are really the thing that you want to shoot for, if you can, as much as possible. And that also might mean padding out your calculation a little bit, having just some no-ops, like a bunch of zeros at the end or something. If that gets you a power of 2 and makes things nice and neat, that little bit of extra work and wasting a couple threads on those calculations will pay off handsomely sometimes if that's what's really necessary. And just something else to point out, in the Snow Leopard OpenCL implementation, at least on NVIDIA hardware, the maximum local workgroup size is typically around 512. So you're not going to be able to have a local workgroup size that's going to be any larger than 512 elements. And in fact, on NVIDIA hardware, I think the maximum number of threads that you can run on a single SM is somewhere around 784, I believe, or something. And there's a point above 512, actually, where as you approach that 700 number, where kicking off more threads, it really doesn't gain you much. there's a reference for that out there somewhere. I couldn't find it, but I know I've seen it or heard it someplace. So that's something to keep in mind. And there may be cases where having 512 threads may be overkill. You might not get any additional benefit from the work group. So you might want to pick some smaller number. So again, you do have to play around with it a little bit more. The last thing related to this question that was posted was dimensioning, where we talked about in the last episode, if you have like an ND range, you can partition problems into 1, 2, or 3 dimensions, and in OpenCL. And the question was, well, why? For example, you can take a 2D image, right, and all of the data might be stored technically in one very long array, but we're indexing, multidimensionally. And I think the point in having that capability is that for scientific problems, sometimes it's just easier to think, and I'm speaking from scientific problems from a scientist perspective, that's all, not that that those are special, but it's sometimes easier to think of the problem as a two-dimension problem versus, as one-dimension problem. And so when you're doing indexing or trying to index into arrays and things like that, it just might make a little bit more sense to think of it as, here's my x coordinate, here's my y coordinate. Okay, this is the, say this is the pixel value I want. Or if you do three-dimensional calculations, say you're doing things on a grid, where thinking of it in three-dimensional terms might make a little bit more sense. There's really no performance gain from doing it one way versus the other, as far as I've been able to tell. So it just might be problem specific. What makes more sense in one way versus what makes sense in one context might not make any sense in the other context. So it's just a way of thinking of things and doing them. So that's work group sizes. Hopefully that answered some of those the questions that were asked. The next thing is problem classes. What are the kinds of problems that canonical scientific problems that people can use OpenCL for, where it might work or might not work? And the examples that were sort of given were like FFTs, BLAS, LAPACK, Monte Carlo simulations, partial differential equations, things like that. For the first three, there are implementations. There are ways to do all of those things on GPUs, and that's actually very and not only to be able to do them, but to be able to do them very efficiently. Partial differential equations, it kind of depends. Some you can do, some implementations you can do very efficiently, some don't. It might depend on your data structures, data layout, and things like that. I'm saying this simply because I know, we deal with partial differential equations in APBS, so it really depends, and sometimes you have to refactor your problem, like where you're just taking data structures, copying them into some more optimal format, doing the calculation, and then copying the results back and things like that. But there are FFT implementations, BLAS, LAPACK implementations. I've seen Monte Carlo simulations done on GPUs. PDEs we've done, of course. So they're all possible and doable. There might be some specifics to the type of calculation you're doing that might make it a little bit more complex or impossible to do. So a lot of that you have to do on a case-by-case basis. But these are all tractable problems on a GPU, and in a lot of ways you can do these very efficiently. So this sort of begs the question: well, what is the optimal range, or what sizes of problems can I do? And so then this kind of, in a lot of ways, comes down to hardware limitations. How much RAM can you get on a GPU? Certainly today you can get some graphics cards with up to 4 GB of RAM. So that's quite a bit, but not everybody's going to have that. So you need to also consider, well, I can only copy, I've got a graphics card that has 512 megabytes. That's going to be a limiting factor. And so those are the kinds of things that you have to think about as well. And again, it's very problem specific and specific to the kinds of work that you'd be doing. But again, you know that, and so think of that as some kind of guidance in problem classes. Now, all of that being said, again, not all algorithms or implementations of an algorithm are going to be optimal on a GPU, so there's going to be some tweaking that you may or may not have to do depending on what specifically you're trying to work on. It's sort of the nature of the game in any kind of optimization or any kind of computation problem. The problem with the GPU is that there are very specific things, specific ways that it likes the data sort of laid out, and if you can get your data in that format, you're going to be golden. It'll really your calculations will really shine. And so you may have to do some refactoring of your algorithm or your code, or you might have to modify your data structures a little bit or create temporary data structures where you put the data into before doing the calculation. Now, the last and most important thing is that you might think, well, I'm doing something, a very complex kind of calculation that involves several steps, or where I might have to loop and do a lot of different iterations. And how would that work? And the important thing to keep in mind is that computations do not need to be run in a single kernel or Q call. So you can break these things up into multiple kernels or multiple Q calls, and it'll work. You'll take a little bit of a performance hit between Q calls, but it's not a huge amount, especially again if you have a problem that is very computationally intensive. So you have to do a little bit of trial and error, but you can certainly get this working. And so let me give you a really quick example of a computation that you might break out into multiple kernels or Q calls. And so in this case, we're looking at this is a conjugate gradient algorithm. And so one of the things, anybody who's familiar with conjugate gradient or these kinds of calculations, you'll note that there are several discrete steps that you would do. And on a CPU, you can sometimes merge these things together or do special things because you have access to all of the memory at once, and things can share information a little bit easier. On the GPU, it's a little bit different. And so what you can see is that, for example, there are Saxby operations. In this case, there are 3 of them. 3 Saxby operations. So you would create one Saxby kernel, and then you would just change the arguments to that kernel and the kernel invocation depending on which step of this you're doing. You can see that we're doing some vector multiplication, vector matrix multiplication, things like that. So you might have to generate a special kernel for that or whatnot. But the point being that you can go and you can queue up all of these types of calculations, and you can execute them, and then you can execute them in order, the way that you would do it on a CPU. The one thing that you have to keep in mind, for example, in this case, certainly conjugate gradient, is there are cases where you'll be doing calculations, and the calculations will say, is there an early exit condition? Have I converged, or have I done what I'm supposed to do? And the problem with those is that once you queue something up into an OpenCL queue, it has to finish. It's there, and there's no way that I know of, at least, to pull something out of a queue or to terminate early. And so if you're doing conditional checks, what you really want to do is you want to maybe say, let's do 10 loops of conjugate gradient minimization, and then let's just do a check. Let's sum up everything, look at our residual over on the CPU, because that might be just a single value that we have to send over to the CPU. A couple bytes of data, check it. Oh, is it done? No. Okay, let me do another loop, or another 10 loops, or something like that. So you have to think about things in that regard. It's best if I have to do a minimum of 200 iterations, then do 200 iterations, and then go check. And if you have to do a few more, then go do a few more, something like that. But the more work you can do without interruption, the better. So that is something important, really important to think of when you're talking about things like molecular dynamics and these types of calculations. Electrostatics, we have similar problems in electrostatics as well. You need to think of those kinds of things. So hopefully that gives you a little bit of a better idea in terms of problem classes. And I think over time what you'll see is, as we go through the tutorials, or as these tutorials, this podcast continue, you'll get a better feel for the kinds of calculations that you can do, and the data layout, and how you go from one form to another to make things work a little bit better. And then also you'll also get a better feel yourself in terms of, this is applicable to me, or this won't work for me, things like that. So hopefully you'll get a better feel for this as time goes on as well. If it's not, if you're not like, I got it. So what I'd like to do then is move on. We'll do an OpenCL example this time, and we'll have a real project. You'll be able to download the project from the MacResearch.org website. If you have Snow Leopard or Xcode, you can launch it, run it. It's nothing fancy. This is in fact a very, very bare bones project, and I did this very intentionally because a lot of the other example code that you might see on the Apple website or in other places, they're very complicated. They're trying to show you, all of the stuff that you can do, and I think in doing that, sometimes things get a little bit more. It makes it a little bit difficult if you're coming into this, from the get-go. If you already are somewhat familiar with this kind of stuff, you're going to be bored senseless. But I think this would provide a nice framework for people who are looking just to kind of get a little bit to get a bit of a feel for how the code is, and what's going on, and how it looks. So this will run on Mac OS X Snow Leopard. Got to have it. You need to have the Xcode tools installed, and like I said, it's a very simple example just to kind of get you familiar with some actual code, and get you familiar with the tool chain. So what I'm going to do first is I'm going to before we go and go through the code itself in Xcode and show you the layout, I want to talk about a few sort of functions. We talked about some of these functions either in episode 1 or episode 2. I can't really remember, but I want to go into some of these in a little bit more detail, just so you get a bit of an idea of some of the things that you can do with these functions, and so you can kind of understand, more, sort of the power, and how you figure out, okay, this is, what the hardware is capable of, and things like that. So the first thing that we're going to talk about is, discovering devices. So the function is CL get device IDs, and overall, this is a very sort of simple. It's a simple function call, but what's important, what you'll notice here are there are probably 3 elements that you really want to focus on. The second parameter to this function call is, what type of device are you looking for? By default, you may be wanting to look for the CPU device, but you can also look specifically for the GPUs only. You can look for accelerator devices, so something like that would be something like an FPGA, or I believe the OpenCL spec references the cell processor as being defined as an accelerator. So things like that would be an accelerator. If there's a multimedia chip, something very specific, that might be an accelerator as well. You can ask the implementation, what's the default device? Whatever the implementation is specified as being a default type of device. Or you can say, just give me everything that's on the system and let me know. You also specify the number of devices you're looking for. You might just be looking for one very specific device. If you're looking for one, that's easy. If you're looking for multiple ones, or you just want to get a list and then parse through that list to see, oh, this is the one that I really want, you can do that as well. And you do that by passing in either the address to a CL device type, or to an array of devices, or where the devices would be stored, and then you'll get those back by saying, okay, I want the top 3, or I want the top 2. If you have, say, a computer that has multiple graphics cards in it, return all the graphics cards, and then I'll figure out which one's the fastest, or something like that. So CL get device IDs. Now, once you have the devices, you want to be able to get information about them. And so, for example, in this example, what we're looking at is the device vendor. I want a string, and the types that are returned are different. Sometimes it'll be an integer, sometimes it'll be a string of characters, as in this case, CL device vendor. But you might want to be probing the hardware to say, what's the global memory size? How much RAM is on my graphics card? Or what's the maximum number of work items? Or for example, if you're looking to see if the hardware supports double precision, you can get a list of the device extensions, and then you can check against that list of device extensions to see, oh, is double precision one of these device extensions that's supported? And if it is, great. I'm going to do my calculation in double precision. If not, then I'm going to have to fall back to single precision, mixed arithmetic, things like that. So CL get device info is what will help you do that, figure out what the device properties are. And there are more options. Those are, again, in the OpenCL spec, and I can't remember if I mentioned this or not already, but we may have one podcast, like I said, if I did say already, that where we go through the specification, just so people can kind of get familiar with it. But check it out. There's a lot of really good, useful information in there, and it's really not that hard to read. So they've done a really good job with it. So check that out. Now, when we're building programs, CL build program, very straightforward. There's nothing very complicated about this. You can read the spec. But once you build the program, you might want to get the program build information. So, for example, say you build a program and you want to look at the log. Say there was an error that happened, and you're like, what was this error? Well, the compiler, when it compiles this, it does JIT compilation, so it's doing it at runtime primarily. You want to say, okay, this failed. Why did this thing fail? You can look at the build log. The build log might tell you, wait a minute, there's a syntax error in your kernel or something like that, because by and large you cannot compile your kernels outside of OpenCL. I mean, I'm sure there are ways to do it. I haven't learned how to do it, so I'm not really certain one way or the other if you can do it. I always do mine just in time when the program is executing. So. But anyway, so sometimes it's hard to tell. You might just have overlooked putting, a comma or something or whatever, or you specified the wrong data type or something like that, and so the compiler might have thrown an error. You can check the log. You can also look at what the build options are and what the build status is in terms of the program build. So there's ways to figure out what has happened during your build with using CL get program build info. There's also memory buffers. When we have memory buffers, and there's two types of memory buffers. There's the memory that's on the host, which is our input data, typically. We may be reading this from disk, or we may be calculating it someplace else, in some kind of calculation, and then we want to do something with it. But to get it on the device, we have to use a very special buffer, and these are CL memory object buffers, and those buffers are tied to to the context that you're performing your calculation in. Now, there are different types of memory that you might say allocate, and so in this case, we're talking about allocating a memory buffer that's read-only, meaning that when we execute our kernel can't write into this memory location. And there may be reasons that are hidden by the implementation, so they might be opaque to the user, where it's more beneficial to use read-only memory versus read-write. So they might be doing some caching behind the scenes in terms of where they store memory. If it's read-only, it might be in the constant cache or something like that. I'm not too familiar with what's going on in the implementation and why one would be more beneficial than the other, but it's probably something like that. And then also you could have read-write memory, you could have write-only memory if you're only writing results to it, and you don't need to say an array, but you never need to read them back while you're on the graphics card, or in a kernel doing the calculation, I should say. There are other types where you can reference memory that exists on the host, so you don't even copy it over to the GPU. Now, again, you don't want to do this. That would be madness to do, because if you're running on a GPU, because it's just going to be slow. Your data is transferring over that PCI bus, and that's just, it's just horribly slow. So, but if you're on the CPU and you're only staying on the CPU, there might be some benefits to that. So, those are some of the options for memory buffers. Now, continuing. When you create the memory buffer, but you need to also write the memory buffer. There's another version of that function, I'm pretty sure, that will do the creation and the writing, but there may be benefits to not doing that simultaneously. And one of those benefits might be that you want to create a whole bunch of memory buffers and then queue up all the writes at once and then force them over to the GPU. It might be a little bit more efficient. And actually, there are also some other more advanced functions where you can do asynchronous copies and things like that, but we won't talk about those for right now, or any more about those for right now. But in this case, you have two options really with the CL and Q write buffer, where we either want this value CL true or CL false. If CL true for the write is given, that means it's a blocking calculation. We block until the write is complete. And that's important because, or it may be important because you want to make sure all of your data is over on the device before the calculation actually starts. If you specify CL false, that means that things, it could be continuing to write the buffer while your kernel kicks off. Your kernels are kicking off, and they might be reading. So some of them might be reading the wrong information or no information. So it's something to think about and consider that when you're writing these things. So CL and Q write buffer can be either a blocking or non-blocking, and it's either, if it's true, it's blocking. If it's false, it's a non-blocking kind of calculation. The next things are execution and read. So we know that we have to set our kernel arguments. This is pretty straightforward. There's nothing terribly complex about this. The enqueue_nd range kernel, where we might specify a specific kernel. So let's say we might have an array of kernels. We may have 5 kernels in our program. In this case, we're going to pass off the first kernel, and because say we're going to run this on the CPU, let's say. We pass in a global work size, but no local work size. Now, if this were to run on the GPU and we don't pass in a local work size, the OpenCL implementation is going to decide for us. And it may get it right, and it may find the most optimal. In my experiments in earlier invocations of OpenCL on Snow Leopard, back before it was back when they were still working very heavily on this, getting it in, the what the OpenCL implementation would actually decide for the local work size was pretty good in terms of finding the most optimal one. So I don't know what they're doing to figure it out, but it seemed to work pretty well, because if I go in and manually set it and then look at timings and things like that, it was often hard for me to sort of beat it. But there were but there may be cases where you're doing something very specific in your kernel, where you're using shared memory or things like that, and you need to limit the size, or you need to pick a very specific size for your local work size on the GPU. So that would be times where you might have to play around with that, with those values, and experiment a bit. And then, of course, we do the calculation, we do it on the graphics card, but we really need the results back over on the host. And so, I mean, unless we're going straight out to display, but by and large, we're probably not if we're doing this. So we also need to enqueue a read, and again, CL true or CL false means that it's either a blocking read or we just don't wait. By and large, you're going to be doing blocking reads, would be my guess, because you want to make sure you've got everything read out before you go and start doing something else with the results. You want to make sure you have them and that you've read them into whatever array you specified. So what I'd like to do now is I'd like to I'm going to switch over to Xcode, close out of this here real quick, go over to Xcode, and then we'll walk through the Xcode projects just so you can get an idea of what's going on. So this is our Xcode. This is a standard Xcode project. This is a little utility that you'd run, say, on the command line or something like that. And like I said, this will be posted on MacResearch.org, so you can download it, play with it, take a look at it. Basically, the only framework we have to include is the OpenCL framework over here. And we've got, as our source, we've got the actual C code that gets compiled by the compiler once to produce our executable. And then we have our OpenCL kernel, which gets compiled by the by LLVM at runtime. So this is what's actually going to be doing our calculation. This is an add kernel, so it's very very simple. We've seen these in previous episodes. So let's just walk through this really quickly. And I've tried to sort of annotate things just so it's kind of clear what's going on. But a lot of this, I'm sure, is very clear to most of you. So our problem size in this case is going to be small. It's going to be 32. Now, if you were going to do an add of 32 elements, and you said, okay, I'm going to go do this on the GPU, you'd be absolutely nuts. Because by the time this got back from the GPU, the CPU would have finished this 1,000 times over easily. There's no point in doing that, but this is just for illustrative purposes. So we set a size, we allocate some memory, some arrays, fill them with some values, and then we call run CL. Now, in run CL, we're passing in our variables, things like that. We have, we're creating a program. We might have two kernels, let's say, but we actually are really only going to use one. We have one kernel in our example over here. We're going to build up a command queue, contacts, devices, things like that. And so I've tried to organize these things in blocks. You don't need to put in these pragmas, and you don't need to put in these braces or anything, just to kind of focus your attention on the different things. So again, device information, CL get device IDs. What you typically might want to do is, because you're not necessarily going to know, every computer has a CPU in it, obvious. So you're always going to have an OpenCL capable device in any computer. So it's always best to at least have that as a fallback, just in case. And so you want to set that. You want to pass in a CPU variable. You get a CPU back. You get a CPU device back. Then what you want to do is you want to go actually look for the GPU. Let's say we want to run this on the GPU. We want all this amazing performance and blah 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 and all this kind of stuff. So you go ahead, you set this up, and then you check. You say, is there a problem? If error did not come back as successful, then set my default device to actually be my CPU device. Okay, and then let's just assert that we actually have a device before we continue, so we don't wreak havoc on the system. And then what we're going to want to do is we're just going to print out a little bit of information to standard out. We're going to probe the hardware device. This will hopefully be our GPU with the device vendor and the device name. Print that out, make sure everything's working what we want to do. After that, we set up our context and command queue. This is straightforward. These are just straightforward function calls. Nothing really specific about this. The context is always tied to the device, so you need to at least do that. And then your command queue is tied to the context and device, so both. And so so that's that part. Then what we're going to do is we're going to say, okay, now let's build our program. So we have our file. Now, here's the important thing. I think this is where some confusion may come from and where people might get, a little concerned even. OpenCL kernels are basically they're read from a file, and they effectively boil down to just regular C functions. There are multiple ways of bringing in OpenCL kernels into the program. They could be as an external file like we have here, which I think is a little bit neater and easier. You can also create C strings and inline those into your application somewhere above, and then load those in that way. There are pros and cons to each one. If they're separate files, it's just cleaner to look at, and it's a lot easier to kind of see. When you make them into C strings, you have to quote them and things like that. It can make it a little bit tough to debug the code if there's a problem, and so I personally don't do that, and I don't recommend it. But this brings up two important questions. One is, well, what if I don't want people looking at my kernels? Fair enough. And what if and is there a performance hit if I'm constantly loading these things from disk and I have to do this every time? So let's address both of those. If you are protective of your kernels and things like that, you can pre-compile them, which I'll talk about and you can create a binary. I know you can do this. The specification supports it. How you do it, I'm not really certain, but and I'll talk about that a little bit more in a second. The other thing, though, is in the context of looking at like the C strings or whatever, where we're I don't know. It's just kind of a mess, and it's really tough to figure out what's going on when you're debugging. You can do it later, and if you inline them, for example, then somebody's going to have to run strings on your application, and then they may or may not see them, but it might be a little bit more garbled, and it might be one way of sort of obfuscating those things for the user. So that's one thing. Now, this issue of compilation, whether you want to precompile or do it just in time, there are pros and cons to both. Obviously, if you want to just ship a binary and you don't want people looking at your stuff without having to disassemble it or anything like that, then that's what you can do. That's certainly an option. The problem with that, though, is that you lose the benefit of the compiler to make the right decision at runtime for the hardware it's running on. So that is, you may have two people running your application, both on NVIDIA cards, where, again, warp sizes are both 32, but one of them might have some special feature that the compiler might know about. And this is LLVM is what does the compilation, the JIT compilation. So that might know something specific, and it might be able to do some special optimizations that you wouldn't be able to do on the other one. So by doing these things at runtime, you're always guaranteed, or hopefully you're guaranteed, to get the best sort of compilation out of your program. And then people are saying, well, if I'm trying to do things fast, why am I wasting time? Recompiling this just seems silly. Well, the compiler is very fast, and of course there is overhead, but there's often times in your program where you're just doing other stuff, and that setup is very slow, and before you get to the meat and potatoes of doing your calculation, and so you might just be able to sort of absorb the overhead of doing that compilation at those points. So it may not really be that big of a deal. Or your program might, stay, running, all the time, and you just reuse the program over and over and over again or something like that. So you compile it once, you do it, you take the hit, but, it might not be that bad. If you're doing Hello World, you're right. It's not really worth it, but it's not really worth going through the effort for this anyway. So this is really, again, designed for really big problems. So that's kind of the point that I wanted to make here, is that there are pros and cons. You're aware of some of them now. Hopefully that will help sort of guide your decision in terms of what you use. So basically, we load the program code from disk, and we create an actual program file. Then once we create the program file, we need to build the program. This is where we do the actual compilation, and if we wanted to, where we would go and check the build info. Say if something went wrong, we could just copy and paste in that function and look to see, I forgot, again, I forgot a comma, or I didn't pass in enough arguments to the kernel or something, or to one of the kernels or something like that. And then once we have our program, now remember, our program can have multiple kernels, so we need to create kernel objects for each single one of those. And what happens is when we create the kernel, it'll go and look and say, what is the name of the kernel, or effectively the function that I'm looking to build or to create. And so let me take that and then take that chunk of code and assign it to this CL kernel, and it's now tied to that. So if I want to invoke a Saxby kernel or an add kernel, I assign it here, and then I just recall that kernel, and I might just have to change the kernel arguments or something like that. So then continuing down, we're doing memory allocation as we did before. We create our buffer. This is an input array that we're bringing in here. So this is going to be read only. We're never going to modify it. We enqueue a write into the command queue. We're going to write into our newly created buffer, and we're going to be writing from this A array, this A value, that a set of values that come in, and it's going to be a blocking write. Okay. Now that doesn't mean that once we've done this and we move past it, that the enqueue write is actually going to happen. The command queue can dispatch these at any time. Okay, and that's important to know. So what we do is we do the same thing for the other one, and then we also create a content buffer where we want to store our results. But in this case, you'll notice we're not doing any enqueue writes because there's nothing to enqueue. I mean, who cares what the values are now? We're going to overwrite them later on anyways in this buffer. So and we're setting it to read write. It could be write only. Then the kicker here, though, is that we issue this command, CL finish, on our command queue. And basically what this says is that if you haven't, whatever things you have in queued that you have not taken care of yet, do it, and I'll wait. I'm going to sit here and wait until you're done and everything is in queued. So by the time you get past this point, you know that everything in this program and everything that was in the command queue has been addressed by OpenCL. So then the next thing that we'll do is we'll set up our kernel arguments. We're going to be passing in, let me open up the kernel side by side so you can kind of take a look. Our first argument is the A array. Our second argument is the B array. Now remember, these are now CL mem objects, but we address them internally as their intrinsic data type. Okay, and then we also have a third memory object, which is what's going to hold our answer. Again, we address it internally as the type of data it is, but we pass in the memory object that we've created up here. Okay, and then once we're through that, and if everything looks okay, all of our arguments were set properly, then we go and do the execution part. We set our global work size, in this case, to n. That's the number of elements we want to process, and in this case it's 32. We're running this on the GPU. We could break this down into multiple local work sizes. We're not, because it's just a single one. It's a 1D problem, and it's a very small problem. Breaking it up would be it just doesn't make any sense. We enqueue this, but again, the enqueue isn't necessarily a blocking enqueue. So we tell CL to finish. Enqueue whatever, but now I'm going to wait. I want this done before I proceed and do anything else. And that's important. You need to make sure that your command queue is completed before you try and read the results, for example. And in fact, if you were to comment this out, there may be circumstances where this will have been enqueued. You'll go to do the read and you'll get the wrong result. And you can play around with that to see, how that happens and how these things, pass through. And so we read the buffer, and then when we're done, we do another CL finish just to make sure that all of the results are done, and then we just kind of release this stuff. And then at that point, since we've read our results from the answer back into the results array, and control is returned back to main, we can now read the results, print the results out to screen, and then just do some memory free up. And I think here actually I think I may need to do some releases here. I need to take a look at this. So the code might be slightly different when I post it up there. We might need to do some freeze here for the buffers. So anyway, so this is basically the function, and so if we were to just kind of run this, what you can see had happened was it went and connected to the device, and then silently it built the program, did a few other things, did the calculation. We get 32 across the board, which is what we would expect given the input values that we've put in here. So it worked. Okay, so hopefully that's clear, and hopefully that helps. But certainly, poke and prod through this and look around, give it a try, and see what happens. The one thing I'd say is that if you go and you make this some very, very huge number, of course, make sure you have enough memory on your system, and then turn off the prints, because it's iterates through the array. So if you set this to 10 million, you're going to get 10 million values printed out in the debugger console, which you really don't want. So just be aware of that. So let's switch back here really quickly and then finish up. So that was basically the demo. Hopefully things are a little bit more clear in that regard. And what I'd like to finish up with are just a few more, just a couple things. Again, all of this information is posted on the MacResearch.org website. Feel free to grab it. Any of the other things, if you have questions about a particular episode, you can post the questions there. Of course, you can email me. Also, again, if you find these things useful or helpful, please, and you have something that you might be interested in getting through Amazon, we have an Amazon store. Please, you're doing us a huge favor. A lot of people bought Snow Leopard through our Amazon store. It's a great help. We really appreciate it. Even other things as well. Some people bought, software and books and things like that. So that's really, really helpful, so thank you very much. The other thing I forgot to point out actually earlier is that there was this great paper that was put out at the end of December by Nathan Bell and one or two other people from NVIDIA on sparse matrix vector multiplication on GPUs. So if this is something that you're interested in, they talk about the different storage formats, the different optimizations, single versus double precision. Very, very well written, very well done. I encourage you to check that out. It's one of the things that I had actually referenced when I started doing some of our matrix vector, when I was optimizing some of our kernels and things like that. And so really, really good stuff, very approachable. They've done a spectacular job with that. So check that out. And then also that other the other presentation online on mixed precision arithmetic. So I encourage you to check those two things out. I think they're both very interesting and worthwhile reading. And so with that, we'll end this podcast. Again, if there are questions or comments, certainly send them my way. And we'll see you next time, where we'll probably talk about data layout, and we'll talk about like warps and memory access and things like that, unless something else comes up. But that's the plan for right now. So hopefully you enjoyed this. Hopefully it was informative, and we'll see you next time.